Hi, welcome everyone to the fifth lecture of the subject control system. In the previous lecture, we discussed about time constant form of transfer function, and then we derived the transfer function in time constant form or in pole zero form of some series RC circuit and series RL circuit, and then we derived the time constant of the RC circuit and RL circuit. Now today, let us discuss further. Let us consider the same circuit, the same kind of circuit, that is RC circuit, but instead of series, today I am going to take a parallel RL circuit. Okay, let me draw the parallel RL circuit or RC circuit. Let me first discuss RC circuit. Okay, now if I consider this output voltage, the voltage across the capacitor as output voltage, then obviously and the voltage across the total thing as input voltage, then obviously the input voltage and output voltage will be same. So there is nothing to analyze. Now I said earlier that capacitor actually stores charge in terms of voltage. That's why we consider voltage across capacitor as output. So let's not disturb the voltage across the capacitor. For today's lecture, I am considering voltage across the capacitor itself as the output voltage. Now in case of input, instead of using the voltage, I am attaching one current source, IT, and this IT will be the input here. Today my system will look like this, and IT is the input and V naught T is the output of the system. So how the transfer function will look like? Let us first convert this into its Laplace domain, the circuit into its Laplace domain. So the current source will give you as I of S, and then resistance will be R itself, capacitance will be 1 by SC, and the voltage will be V naught of S. So in Laplace domain this will look like this. Now what is V naught of S? Now V naught of S is the voltage across this impedance. Now so if the current across this impedance is IC of S, then V naught of S will be obviously IC of S into 1 by SC. This will be the equation. Now how we can find ICS? Obviously by using current division principle. So using current division principle, total current into opposite impedance by the total impedance. Let me evaluate it. I of S R by RSC plus 1 by SC, and this SC will appear in the numerator like this, RSC. So V naught of S is now equals to I of S into RSC by RSC plus 1. Now what will happen is RSC, now IS is the input variable, Laplace transform of input, and V naught of S is the Laplace transform of output. So we can define the transfer function T of S equals to V naught of S, sorry, by I of S, and this will be RSC by RSC plus 1. This will be the transfer function. And consider the time constant form. It is numerator by the denominator was S tau plus 1. So what is the value of tau? Is RC. So no matter what the circuit configuration is, whether it is parallel RC or it is series RC, for an RC circuit the time constant will be always the product of the value of R and the C. That will be the time constant of the circuit. Now consider another circuit. Similarly, as we have seen earlier, that for series RL circuit the time constant was L by R. Now let us see whether for parallel RL circuit the time constant is L by R itself or not. Let us consider the system R, then L, okay. Again, what is the thing here? I said earlier that the inductance actually stores magnetic energy in terms of current across it. So the current across an inductor will be the output voltage. Let us not disturb it, as in the previous case. The voltage across the capacitor was taken as output itself. So the current across the inductor will be taken as output. Now what will be the input? If the input is an input voltage VIT, then obviously the current will be VIT, the total voltage VIT will be appearing across the element L, and the current will be just voltage by the impedance. So there is nothing much to analyze. Hence, as the previous case, I am considering one current source here to denote the input. Let us consider IT is the input. Okay. So first convert it into Laplace domain. Obviously, this will be II of S. Then this element will be R, and this element will be L. Sorry, this element will be SL, as the elements are replaced by their corresponding impedance values, and the output will be the current through it, I naught of S. So again, I naught of S is equals to total current I of S into the impedance, the opposite impedance by the total impedance SL. So what will be the transfer function? The output by the input, that means I naught of S by I of S equals to T of S equals to R by R plus SL. Again, if I take common R from here, and it will look like S into L by R. This R gets cancelled and it will look like 1 plus S into L by R. So again, the transfer function is now 1 by 1 plus S into L by R, 1 by 1 plus S tau. Compare these two form, and tau will be L by R. Though the time constant is dependent on its on the input variable, which variable you are taking as input, or which variable you are taking as output, the time constant pretty much depends on that. But if the time constant is there, for RL circuit the time constant will be L by R, and for RC circuit the time constant will be RC, whether it is a series RL or a parallel RL. Okay. Now this was the analysis of circuit portion. Now we can solve some examples based on that. Let us consider an arbitrary circuit. Let us draw an arbitrary circuit. Okay. A resistor here. Let us say here is an inductor L1, another inductor L2, and here is some capacitor C, and the voltage across this is output, voltage across this is input. So let us analyze this circuit. Okay. As it is in time domain, it will look like this. Okay. Now analyzing this, I am not redrawing the circuit again, rather I am replacing each element by its corresponding impedances. So L1 the impedance will be SL1, for L2 the impedance will be SL2, for C the impedance will be 1 by SC. Now the circuit can be represented like this, some Z1 here and some Z2 here, and here is the output V naught of S. Okay, now it is in Laplace domain, so the output and input variable will be in Laplace domain. Now you can easily calculate V naught of S by Vi of S is equals to Z2 by Z1 plus Z2. Please excuse me, I need to fill my refill. Z1 is simple, the series combination of R and SL1, so R plus SL1. And how we can calculate Z2? Z2 is the parallel combination of SL2 and 1 by SC. So let me obtain this one, SL2 into 1 by SC by SL2 plus 1 by SC. L2 by C, and this will be, okay, let me erase this one, L2 by C. I think this is not clear to me. S square L2C, S square L2C plus 1 by SC. Now C gets cancelled and S will be there, SL2 by S square L2C plus 1. This is Z2. Now V naught of S by Vi of S is Z2 by Z1 plus Z2. So what is Z2? SL2 by S square L2C plus 1, and for Z1 R plus SL1 plus SL2 by S square L2C plus 1. I am not doing the whole calculation here. I hope you can do that easily. This is how the transfer function can be obtained for any circuit. First, convert the circuit into its corresponding Laplace domain, and then by using basic laws like voltage division principle or current division principle or Ohm's law or Kirchhoff's law, you can use those laws, those physical laws, and then from those physical laws you can derive the equations, derive the transfer functions. Okay. I think okay, let me take another example circuit and analyze it for the last time. Another example circuit. Let us consider a parallel RL circuit. Okay, RLC circuit, but parallel. Earlier we have seen a series RLC circuit, and then in the first lecture when we introduced the term transfer function, I guess in the second lecture, there we discussed the transfer function and by taking an example, and the example was a series RLC circuit. Now I am considering a parallel RLC circuit, and then I am considering as it is parallel. So if I use voltage as, if I consider a voltage in input side and that is to be an input variable, then the output will nothing like if the output across the capacitor, the voltage across the capacitor is output, then it will be equal to input. If the current through the inductor is the output, then it will be the voltage will appear across the inductor and the current will be voltage by its impedance. So this will be pretty simple. So to do some analysis, I am considering one current source as input variable, IIT, okay, and I naught t will be the output of the circuit, that is across the through the inductor, the current through the inductor. So again we can consider we can transfer this circuit into its Laplace domain like this. I of s, R will be replaced by R itself, C will be written as 1 by SC, and L will be replaced as SL. I naught of capital I naught of S will be the output of the system. So how we can derive the transfer function? Again, the transfer function will be the current this current by this current in Laplace domain. So again, using current division principle, I can obtain this thing. So I can actually consider this circuit like this: Z1 and Z2. Okay, and current through Z2 is my output, this current is my input, and Z1 is the parallel combination of R and 1 by SC, and Z2 is SL itself. So what will be the value of Z1? Z1 will be R by SC by R plus 1 by SC equals to R by SC, RSC plus 1 whole by SC, and SC gets cancelled, so it will look like R by RSC plus 1. This will be Z1, and Z2 as we have written SL. So what will be the value of IOS? I naught of S will be equals to the total current I of S multiplied by the impedance which is not in action, that means the opposite impedance, that means Z1 by the total impedance Z1 plus Z2. Let me erase this portion. So what is the value of Z1? As I have calculated, Z1 is R by RSC plus 1, R by RSC plus 1, Z1 R by RSC plus 1 plus Z2 means SL, I naught of S. So the transfer function T of S will be I naught of S by I of S, that is equals to this expression. I am not calculating this expression in details because this is pretty easy. It is actually some mathematical manipulations. Now you can also consider the output voltage as the output, that means the voltage across the capacitor. Okay, let me do that thing once, it will be fun. Actually it is very easy to solve and it is fun to do. Okay. Let me redraw by arranging the elements R, L and C. Okay, this voltage will be the output. Now how we can calculate this voltage? Again, if we can calculate this current, then current multiplied by its impedance will be equals to the voltage. So how we can calculate the current? Again using current division principle. Now in this case, okay, I am not redrawing the circuit again for representing in Laplace domain, but I am manipulating the variables here only. V naught of s, I of s, R will be R, L will be SL, C will be 1 by SC, and ICT will be IC of S. Now again, this will be considered as Z1, this will be Z2, and Z1 will be parallel combination of R and SL, so it will be RLS by R plus SL, and ICS will be equals to II of S, the total current, into the impedance which is opposite Z1 by the total impedance Z1 plus Z2. II of S, Z1 as I have calculated RLS by R plus SL, and Z1 RLS by R plus SL, and Z2 will be 1 by SC. This is II of S, sorry, IC of S. Okay, again now V naught of S equals to 1 by SC into I naught of S, sorry, IC of S. V naught of S equals to 1 by SC IC of S. So IC of S can be written as V naught of S into SC. V naught of S into SC equals to this expression, II of S RLS by R plus SL total by RLS by R plus SL plus 1 by SC. And the transfer function will be V naught of S by II of S equals to 1 by SC, and this total expression. Again I am not calculating this whole expression because it is easy to calculate, it is just mathematical manipulations. So this is how we obtain transfer functions for electrical circuits. Now next thing I am going to discuss is some physical system modeling. For today's lecture I will deal with only translational motion. I am not going into rotational motion as of now. Okay. So what is the modeling technique? Actually what happens is, any physical object can be represented in terms of some mechanical blocks, not only blocks, some mechanical objects. Any physical system can be represented in some of in combination of some mechanical objects, and the fundamental three mechanical objects are there. One is mass, okay, another one is spring, another one is damper. Mass will be represented by M, spring will be represented by K, and damper will be represented by B. Okay. Now what is these three things? Mass, actually any object, any mechanical system can be transformed into some equivalent, like any circuit, like let's say for op-amp. I think you have studied the subject analog electronics. Okay. Excuse me please. For analog electronics, you might have seen that any transistor amplifier can be, any BJT amplifier can be modeled into some can be modeled by means of some electrical systems, and that electrical circuits that electrical circuits will consist of only 3 elements, that is R, L and C. So any physical system can be represented by some mechanical equivalent, and that mechanical equivalent will comprises of these 3 elements: mass, spring and damper. Okay, like an op amp. I hope you have seen an electrical equivalent circuit of an op amp. So that equivalent circuit will consist only some source, some dependent or independent source, and some elements like resistor, capacitor and inductor. These 3 fundamental elements can be represented, and by some suitable interconnections can represent any physical system or any electrical or electronic system. And for physical system we have mass, spring and damper. Okay. Now I am elaborating this concept by some example. Let me tell you one thing. We are studying the subject control system, so we need to know the different kind of mathematical modeling that is involved in the industry, but we will not go deep into how we can create that equivalent mass, spring, damper diagram of any system. We will not go deep into that, but if you have given me some mass, spring, damper diagram, then from that diagram I can calculate the transfer function, or I can calculate the differential equation that governing the system. Okay, so I am not going to discuss how we can model that into mass, spring, damper diagram, but from mass, spring, damper diagram how we can analyze that system using obtaining some transfer function or some differential equation. Okay, so let me take one example. It is the most fundamental example that everyone takes, is a simple mass, spring, damper system, a mass which is connected through a spring and a damper with a wall, and some force is applied and some displacement is happening. Now what is the system comprises of? The system actually comprises of only these 3 elements. And what is this variable and this variable? As obvious, the force is the input variable and x is the output variable. Okay, the displacement. Let us consider this scenario. Let me redraw it. Okay, now one force is applied, one displacement is happening. Now look for this system. By using physical laws we are going to arrive to the differential equation of the system. Now what is the relationship between the input output in general way, as the mass have equation of motion as resultant force will be equals to mass times the acceleration. This is from Newton's law. Now again, spring has some has its own some properties. Like for spring, by K I means this I mean the spring, okay, and by B I will mean the damper. So what is the spring? The spring, let me draw a diagram of a spring. Let us consider this is a spring. Now if one end of the spring is fixed and you are pulling this end of the spring, then that spring will oppose your pulling. Okay, you are applying some force F, and then the spring will apply some restoring force F again in this direction to oppose the elongation of the spring. So this F is called the restoring force, or instead of Fr I can call it Fk. By Hooke's law we know that this opposing force, this is called actually restoring force. This restoring force of spring will be proportional to the displacement that is happening to the spring, or the elongation that is happening, elongation or compression. Let us consider you have a spring and you are pushing this spring towards left. So the spring will be compressed by some amount x, and it will exert a force on your hand in rightward direction, and that force will be proportional to the amount of compression, that means to x. For elongation it will act like act in this direction, because you are elongating the spring in this direction, it will the force will act in this direction, and if you are compressing the force you are pressing it in this direction, so the restoring force will be in that direction. Whatever be the direction, that will be considered when I am going to derive the differential equation of that system. But for now, just consider the magnitude. The magnitude of the restoring force will be proportional to the compression or elongation, proportional to the displacement of this tip. Okay. If this is fixed, then the displacement of this tip itself will be the elongation or compression. If it is in this direction, that means in this direction, then it will be elongated, and if it is in this direction, then it will be compressed. This amount will be x. Again, so now Fk is proportional to x. Now by Hooke's law, this is proportional to x. Now we actually consider one proportionality constant k here, and that k is called the stiffness of spring, stiffness constant of spring. More the k, more will be the force for same compression, and the stiffness will actually, when the stiffness increases, you need to pull it harder to elongate it. Okay, because small x will result large restoring force, because the k will be large then. This is called stiffness constant. Now consider this tip. Instead of being attached in a wall, this end is also free, and let's say this end is having some x1 displacement, and this end is having some x2 displacement. So you are pulling that spring, this end is having some x1 displacement and this end is having x2 displacement. So there will be some net elongation happening, and that net elongation will be x1 minus x2, right? So the compression force will be k into x1 minus x2. Compression force, that will be the restoring force, the spring exerted on your hand. Okay, so this is spring. Now what is damper? Damper actually defines the friction that is involved within the system. Okay, and that damper we can consider the diagram. It is a rough diagram. Okay, I don't want to go deep into these concepts, because this is not something from control system, but arriving to the differential equation and analyzing the differential equation or the transfer function is something related to control system. That's why we need to learn this thing. But how this damper works, how this spring stiffness constant is there, how these all things work, and how we can arrive this kind of circuit of mass spring damper from any physical object. Let's say you have some automobile vehicle. Okay, that vehicle will be represented some mass spring damper system. How that will be done, it is not our concern. There is some mechanical engineers to do that, but for control perspective we need the analysis portion of this mass spring damper system. Okay, so what is a damper system? A damper is like, it is also called a dashpot. Okay, let us consider this is a chamber and this is a piston, and here it is some viscous fluid. Okay, here it is some viscous fluid. Now if there is some relative motion between the chamber and the piston, then obviously the viscous force, viscous fluid will exert some friction on the piston or on the chamber wall, chamber inner wall. So any friction in any system is represented by this thing. Now again, as we know, frictional force is actually proportional to the velocity of the system. Now instead of this figure, let me consider the schematic diagram of damper. This is a damper. Let's say this portion of the damper is fixed, and at this end you are applying some displacement by using some force or something like that. Okay, that is not our concern, but you are applying some displacement. There is some displacement happening at this tip. Okay, so now there will be some frictional force, and I am going to call it by Fb. The frictional force, as we know, is proportional to the velocity. So what will be the velocity? The net velocity, that the net velocity will be x, because this end is actually fixed, and again b is the proportionality constant, if b equals to x dot. Again, as in spring, if instead of being fixed, this point is having some displacement x1, x2, or and this point is having some displacement x1, so the net friction will act in this side, will be equals to Fb equals to b into the net displacement in this side. The force will act in this side and the net displacement will act in this side, because the force is opposing the displacement. So the net displacement in this side will be x1 dot minus x2 dot. By dot I want to say that it is time differentiation. Okay, so this is mass spring and damper system. Now how we can obtain the transfer function or the differential equation from this? So let me discuss that thing. So this is a mass spring damper system. Now why what we know from Newton's second law, that is F equals to mx double dot. So what is this F? This F is not this F. Remember, this F is the resultant force. So if I draw the free body diagram of this mass, what will happen? The mass is having some displacement in this direction, some input force in this direction. Now you are pulling this mass in this direction, so a displacement of x is happening in this direction, so the spring will oppose that displacement, so spring will develop some restoring force in this direction, and that force will be proportional to this value x. So the frictional force, the restoration force of the spring will be in this direction, and the frictional force also will be in this direction, because friction will also oppose the displacement in this direction. That means the velocity in this direction, b. Okay. Now what will be the resultant force? The displacement is in leftward. So the acceleration will be in leftward, so the net force will act in leftward direction. So the net force in leftward direction will be F is in leftward direction minus Fk minus Fb. Now what is Fk? Fk is spring constant K. Okay, often it is called spring constant also. It is either spring constant or stiffness constant. Okay, so if we Fk, so it is K into this end is fixed, so the net displacement is x itself, so it is x. And what is Fb? It is b into x dot sorry, mx double dot. So mx double dot plus kx plus bx dot is equals to f. X is output and f is input, so this relationship is the this differential equation is the governing differential equation of this system. Now easily we can calculate the transfer function from this portion. It is okay, I have taken this as capital M and it is a small m, so I am replacing this capital M by some small m. Okay. Now what will be the value? M s square x of s plus k x of s plus b s x of s equals to f. Now x of s is output, f of s is input. X of s by f of s will be equals to 1 by m square plus bs plus k. This will be the transfer function of this system. Okay, I think that time is over now, so I am closing today's lecture. There will be some other examples of a mass spring damper system, and I will obtain the transfer function and the differential equation of the transfer of that diagrams. Okay. So this much for today's lecture. See you in the next lecture. Thank you.